Hello and welcome to Lab 4, Circuits and Capacitors. In this lab we're going to be predicting the values of current and potential difference within a circuit and then testing our predictions using an online simulation. And the purpose of this lab is to observe the relationships between current, resistance, potential, and capacitance and to practice measuring and calculating such values. These are the key principles we'll be using in this lab. We'll start with Ohm's law, which is important for calculating the resistance given a current and voltage. It's important to keep this in mind also for when we want to calculate the individual resistances for the circuit components in a parallel circuit. And this last equation will be important when we're trying to visualize a linear relationship between the potential difference and the RC component, which we will extract from the slope of this graph. So the first scenario we're given is two batteries with voltages of 1.5 each and two resistors of 147 ohms. And when we plug that into our equation that we discussed earlier, we get 0.0204 amps. And when we look at our simulation, that is about the value that we get. So we know that we calculated those values correctly. Now, if we were to reverse the connection on the ammeters, we'd see that, or on one of the ammeters at least, there you can tell it's switched. You can tell the reading isn't any different. Now if we replace one of the ammeters in the circuit with a voltmeter, we see one that the voltmeter reads out a voltage, but that the current is now reading 0 on the ammeter. This is because the voltmeter is a high impedance object, is going to prevent any current from flowing through. If we complete the circuit again and measure potential difference across at different points along the circuit, we see that this first section is measured at 3 volts. The section along the wire is at 0, as will be this section down here. And as we measure each section with the resistors, we find one to be negative 0.96 volts and one to be negative 2.04 volts. When we graph these potential differences according to their corresponding segments, we see that in total they add up to 0. We may wonder why the current reading doesn't change when we attach the voltmeter to the circuit. After all, is it not changing the circuit? Well, this all comes down to the equation that we showed at the beginning. The voltmeter is now a parallel component of the circuit, and since it is such a high resistance object, the component of the total resistance that it contributes to falls to 0, since this R is in the denominator, and so it will not affect the overall resistance and thus the current of the whole circuit. However, if we replace the voltmeter with another ammeter in parallel, we see that this ammeter does change in value. This is because, as opposed to a high resistance object, this is approximated as a very low or even 0 resistance object, and that will cause a change in the total resistance for these two components of the circuit. Now, if we go back to the circuit we had before, we can calculate the resistances at each location by taking the measured potential difference that we calculated earlier at each of these positions and dividing it by the current that was measured. And we get these figures, 48 ohms at the R47 resistor and 102 ohms at the 100 resistor. Of course, these values are slightly different, but they are fairly accurate. A reason for this difference is that the current value is likely rounded for this ammeter. Here we take a look at how the potential difference across a capacitor changes over time when we include a light bulb at 30 ohms resistance within the circuit. When we take the natural log of the ratio of the potential difference and the initial potential difference and graph it over time, we observe a linear relationship, the slope of which corresponds directly to the resistance times the capacitance. In our final calculation, we set the slope of the graph equal to the negative inverse of RC, which ends up being 6, and that is exactly the value that you'd expect when you multiply 200 millifarads with 30 ohms. The last questions we'll ask are, what if we used an actual ammeter instead of an ideal simulated ammeter? Well, in reality, adding anything to a circuit is going to change the current going through because there is some resistance. So the ammeter will add some resistance and affect the current, unlike in this ideal scenario. What if we used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Based on our model, the capacitor would reach full charge instantaneously with no resistance. However, once again, in reality, there is certain to be some resistance in the circuit even without a resistor, so it would still take some time, even if it was very little. In conclusion, we found that the simulation helps us to visualize how the different components of a circuit affect the current and how the potential changes at different points along the circuit. And the ideal model will still differ from reality because real measuring tools like ammeters will still have a resistance when added to a circuit. Thank you for watching this video.